Hi everyone. So today we will learn about spectroscopy, and I'm assuring you that if you continue the whole class and after that there will be not a single question that you can't attempt. Okay, so it's my guarantee that if you continue the class and if you just understand the concept carefully, then you can solve each and every question. Okay, so without any delay, just let's get into the concept. So spectroscopy means that here we are observing, we are using some wavelength. It may be UV, ultraviolet ray, maybe visible, maybe infrared, or maybe uh, some radio. I hope you know the different kind of wavelength, right? So if you see that the radio has the like highest wavelength among these three or four, and then UV visible. So in the visible range that is from 400 nanometer to 700 nanometer, right? So the basic principle is that here one lamp is there. Okay, so all kind of spectroscopy technique are mainly used for maybe quantity or qualitative assays. Suppose if you want to determine some concentration, or if you want to determine uh, any kind of contamination of biomolecule. Suppose you purified protein, then you want to check whether there is some DNA contamination is there or not. So for that kind of purpose, you can use spectroscopy. Along with that, NMR you can use for 3D structure determination, IR for functional group study. Okay, and circular dichroism you can through circular dichroism you can study the secondary structure, alpha helix, beta sheet, various kind of folding, unfolding, like that. So now we will focus on mainly the UV visual spectroscopy, and this is the lamp here. And from lamp, different we know the like violet, green, blue, red, everything here it's emitting everything. Then one monochromator is there. The monochromator will allow only one wavelength. So if there is seven wavelength, but it will allow only one wavelength wavelength. And here some sample cuvette is there, and this wavelength will pass to the sample, and now this sample will absorb some wavelength, and rest of the wavelength will be transmitted, right? And how uh, how much is absorbed, that will be detected by some detector, and then this detector will give some readout. That's the basic principle. So if you see here, this UV visible spectroscopy, in UV visible spectroscopy, this UV visible ray, they are changing the electron. So here, uh, this is the non-bonding electron, right? And this is the pi and sigma. This is bonding, and this is anti-bonding. So if you see the energy, like energy of anti-bonding is greater than the energy of bonding. So if one electron want to jump from this bonding to anti-bonding, so for that it needs some energy. Okay, and that energy will be provided by the UV or visible ray. So whenever from monochromator the single wavelength light is emitting, and that particular wavelength we know that E equals to Hc by lambda. So that is providing some energy, and that energy is utilized here for transferring electron from one to another. So from pi to pi star, from sigma to sigma star, right? So here it's written that the molecule absorbs the UV visible or visible light at specific wavelength corresponding to electronic transition between different energy level, right? So from suppose sigma to sigma star, pi to pi star, and that absorption needs to decrease in intensity. So suppose let's assume here first there was 100. So I am assuming that the uh, incident wavelength is 100. Here where the trans after absorption we are getting 60. That means what? That means here 40 is absorbed, right? and that's how you can estimate the concentration. There is one specific law you will see in next slide, that is Beer-Lambert law, and from Beer-Lambert law you can estimate the absorbance, and also if you get the absorbance, if you don't know the concentration, you can get the concentration as well. Now through UV visible you can estimate concentration of protein, uh, DNA, RNA, different kind of biomolecules, right? And so in general, if you see, so suppose if you isolate some DNA or RNA or protein, in general you have to see 260 by 280 ratio. Okay, what is 260 by 280 ratio? uh, Protein molecule generally absorb at 280 nanometer, and uh, nucleic acid generally absorb at 260 nanometer. So suppose if A 260 by 280 is 1.8, that indicate its DNA. If it's 2, it indicate its RNA, right? If it's near around zero point 0.6, it indicate its protein, right? If the 260 by 280 ratio is near around 1.95, that indicate the sample has uh, DNA plus RNA, that means some RNA contamination is there, right? So from that 260 by 280 ratio you can get to know uh, the about the property of your sample, whether is there any contamination or not. Now let's know about the Beer-Lambert law. What is Beer-Lambert law? The Beer-Lambert law is all about the absorption. So suppose in the previous slide we already saw that whenever some light is passing through some sample, some light is absorbed, right? And few lights are transmitted. So now what's the exact amount of absorbance? Okay, how we will get to know that? So here A is absorbance, epsilon is the molar extinction coefficient. Okay, that measure of how strongly the substance absorbs light at particular wavelength, and you have to remember the unit. That is the letter mole inverse centimeter inverse, right? So if it's liter mole inverse centimeter inverse, and the concentration will be uh, suppose liter mole per liter something, and then you can get to know the uh, absorbance here. So it is the centimeter, and that's the mole liter inverse. So that's why the absorbance is unitless, right? Suppose you can get to know you can get the absorbance 0 0.6, 1.8, like that. The absorbance is a measure of amount of light absorbed by a sample. And what I was telling earlier, that suppose this is the sample, here the light is coming, the incident light intensity is I0, and then when the light is has already passed to the sample, now its intensity is I. Now you can calculate the transmittance. What is the transmittance? T equals to I by I by I0, I0 by I. That's the transmittance. Sorry, I by I0, because here I0 will be more and I will be less, right? Yeah, sorry for the noise. And that's the transmittance, and this is the I, that's this is before transmission, and this is after transmission. So we can also write that log 1 by uh, t, sorry, minus log t, or log 1 by t. We can write in both way. So the transmittance t equals to I by I0. If someone says the transmittance is 40%, that means 40 by 100. you can write by 0.4. So in general we are getting that log T transmittance base 10 equal to epsilon Cl, right? So from here, if someone give you transmittance, you can calculate the concentration, right? Now NMR. So what is the basic principle of NMR? In generally, the NMR spectroscopy relies on the behavior of atomic model. So earlier in invisible there was electronic transition. If you remember, it was electronic transition, but in NMR there is nothing about electronic transition. It's all about the uh, nucleus, right? So in nucleus, so the in nucleus hydrogen 1 or the carbon 13, so these are the non-zero spin. And in generally if you see nucleus, so suppose there are also plus and minus, right? So that will behave a tiny magnet. Okay, so in general these tiny magnets are not properly arranged, they are not aligned. But whenever you will give some external magnetic field B0, they will align themselves and they will work on a specific direction. And when you will apply the radio frequency, and they will be excited from the lower state to the upper state. So I hope you remember there for one spin molecule there are two states, right? Plus half and minus half. So whenever you are giving some radio wave, okay, they will be just transferred from lower energy to higher energy. And the frequency of the RF radiation is specific to the type of nucleus and its chemical environment. That's very important. So what will be the frequency of the RF radiation? That depends on the nucleus and the surrounding, like suppose surrounding electron density and surrounding functional group in broader sense, right? And then after that, when the RF pulse is turned off, the nuclei again come back. Suppose in excited state they just went there, they will again come back if you stop the RF pulse. And then they will release some RF signal. Here it's written as RF signal, and that RF signal will be detected, and this RF signal will be converted to spectra. Okay, so this difference in resonance frequency provide the information about the local chemical environment. That's what I was telling about the different kind of functional groups. Suppose CHO, suppose COOH, different kind of functional group. You can get an idea. Okay, so the basic principle of NMR is that uh, the nucleus is a tiny magnet. Whenever you are, they are quite random, but whenever you are giving some external magnetic field, they will align in a particular way. And after you give, so then you apply the RF pulse. So as soon as you will off the RF pulse, what will happen? Uh, when you apply the RF pulse, there will be transition from lower spin to higher spin. Okay, and as soon as you will turn off the RF pulse, they will again come back to the lower state. And at that time the radiation, okay, it will radiate in the sense of RF signal, and that signal will be captured and you will get a spectra, and after analyzing the spectra you will get to know the structure. So application, you can say that through NMR you can determine 3D structure, okay, and you can get very good resolution as well. And through NMR we know that MRI, magnetic resonance imaging, we can understand the metabolic profile. Okay, that's very important to for diagnostic purpose, to understand like what kind of disease or what kind of disorder is going on, right? And for structure you can determine protein, nucleic acid, everything. But the limitation you should remember, for protein structure determination, NMR is effective only for small protein, small to medium. If you take more than 50 kDa or something, it's quite huge for NMR, because you can get better structure up to suppose 25 kDa, like that. Because as soon as you will take a larger protein, there is too much spectra, too much analysis, it's quite challenging. And you can also estimate the so for one another limitation is that the sample concentration. The higher sample concentration is sometimes required. That's quite not possible because you don't have that much protein. Then how you can determine the structure? It's quite difficult at that case. Okay. Another kind of spectroscopy is infrared spectroscopy. So the IR spectroscopy is powerful analytical technique used to identify and study chemical substance based on their interaction with IR light. So here I have given the exact order. This is X-ray, this is UV, this is visible, this is IR, this is microwave, this is radio wave. So whenever you are going from here to here, the wavelength is increasing and energy is decreasing. Got it? The infrared comes in that region. So uh, in here, yeah, this is the infrared region. So the here in infrared there is no such electronic transition or nuclear transition, nothing is there. So what that depends on the vibration of molecule, right? Is based on the absorption of infrared light by molecule, which causes change in their vibrational energy level, right? Different chemical bond absorb IR radiation at characteristic frequency. So there is some bond like COO. So that this bond has some polarity, and for that polarity, that the bond will be vibrate, right? And whenever you will give that frequency infrared, then it can absorb and it can show the peak, right? So absorption of IR radiation. Okay, so molecule absorb IR radiation when frequency of IR light matches the vibrational frequency of a bond, leading to an increase in vibrational energy of the molecule. That's what I was saying. So suppose if the IR you are applying, if it's exactly same, okay, if it matches the vibrational frequency of a bond, then that will uh, increase the vibrational energy of molecule. So here you can see here, this is the transmittance here, and this is the wave number, wave number. So here all these are for different kind of functional group. So from 1000 onwards you can see this is the fingerprint region. So that's different from different for different kind of molecules, but in general, so the CO bond stage you can find around 1650 centimeter inverse, and for CO, CN, like alkane, alkyne, NH stage, OH stage. So there are specific particular spectra. So through that you can identify which kind of functional group are there. In protein, so suppose NH3 are there. If there's some kind of post-translational modification, suppose CHO, and other kind of modification like gamma carboxyglutamate, something, you can understand it from IR. Okay. So the IR spectrum consists of various peaks, each corresponding to a specific vibrational mode of bond. That's a very important word. That's vibrational mode of a bond or functional group, but it never talks regarding molecular weight. Okay, so interrupting this peak help in determining the molecular structure, and also the intensity of absorption peak can be used for quantitative analysis, right? So suppose you prepared some chemicals, then you should prove that that functional group is there. You can do spectra, IR spectroscopy. So in broad sense, you can identify functional group. Along with that, suppose if you want to study some chemical kinetics or not chemical reaction, and suppose there is some OH and the plus COOH, something is two functional groups are there, then they make some ester bond. How do you get to know that? Through IR you can see the change in spectra. So first for OH and COOH there are some different spectra, and after that for the ester bond there is some different spectra. You can compare the spectra. So through that you can visualize the movement of a reaction. Okay, but the major limitations are the IR transparency. So not all material are suitable for IR, like water. It strongly absorb in the IR region, and that's, so suppose some molecules strongly absorb IR, that will interfere with your analysis, right? And also some commixture is there, it's quite impossible to perform IR. And there is circular dichroism that depends on the plane polarized light. Suppose some lights are there, then we apply some polarizer, then the direction is fixed. This is linear polarization. Along with the circular polarization is also there. Okay, so this is circular dichroism uses a circular polarizer. So it is a spectroscopic technique that used to study optical properties of chiral molecules. So the amino acids are chiral, right? But particularly so they function in UV and visible region. Uh, but remember, CD can perform only for the chiral molecule. So chirality and is the main concept of CD. So the CD measures the differential absorb of left-handed and right-handed circularly polarized light, but by chiral molecule. So one is left-handed. So if you know the circular polarization, so there, so suppose you can just imagine. Suppose this is one circular polarization, and another circular polarization is like that. I can, yeah. So then we can deduct these two. This is suppose left, this is suppose right. We can deduct these two, left and right, and then we can get the uh, ellipticity, right? So through circular dichroism, you can find out secondary structure. In technique, the things only important for you to understand the basic principle and then the application, how you can apply. So the CD generally here you can get to know various secondary structure detail, alpha helix, beta plated sheet, random coil. So here in alpha helix you can see it's showing positive peak at around 195 nanometer and negative peak at around 225 to 22 nanometer negative peak for alpha helix. For beta sheet it's showing positive maximum around 192 and negative will be near around 205. For random coil at that region, suppose near about 195 nanometer, it's showing negative at 195 nanometer. For beta sheet you should understand positive at 192 and negative at 205. For alpha helix positive 195 and negative peak at 222. So through that you can exactly separate alpha helix, beta plated sheet and random uh, coil. So here you suppose some ligand is binding to protein and that lead to some protein unfolding and thermal denaturation that you can study with circular dichroism. Along with that, the circular dichroism can be studied uh, for some conformational property of like DNA, RNA, like various form of DNA, bDNA, zDNA, other form of DNA, and along with that also the protein secondary structure. Okay, now we'll solve question here. That's the main objective of this class. Okay, so here a protein solution of 1 micromolar has transmittance 40% as 280 nanometer. So I am writing here transmittance 1 is 40%, that means 0.4 when measured, and the concentration is 1 micromolar. When measured in 1 centimeter cubed, that is L equals to 1 semi. Using a UV visible spectrophotometer, transmittance of the same solution when measured using 2 centimeter cubed is, that means the C is constant. Now here L is changing and N is changing to 2 centimeter. Now we know absorbance equals to epsilon Cl equals to minus log of transmittance, log 10 transmittance. Now here E constant, C constant, that means minus log 10t varies with L, that means minus log 10 base T2 divided by minus log t base 10 T1 is equals to L2 by L1. Now L2 is 2 centimeter, L1 is 1. So from here you can get to know log T2 equals to uh, okay. So log T2 equals to 2 into minus log T1, that is 2 into minus log 0.4. Through that you can get the value of T2, right? So if you calculate it, it will be approximately 16%. So here what is given, first you have to see the epsilon and the C is constant, only the L is varying. So you know the absorbance equals to minus log of transmittance. So through that you can directly calculate the transmittance at uh, the cuvette length of 2 centimeter, right? Okay, second question. The question is all about the infra-IR spectroscopy is used for determining certain aspect of structure of organic compound. Okay, so the first option is that the IR induced electronic transition. That's really wrong. We already learned that IR is nothing about electronic transition. It's all about vibration of the chemical bond. IR peak intensity are related to molecular mass. That's also wrong. This all about vibration and nature of functional group. Okay, most organic functional group absorb a characteristic region of IR spectrum. That's true, because we have observed that there is specific for CO, there is specific for CN, there is specific for CHO, right? That's true. Each element absorb a characteristic wavelength. Yeah, each element absorbs a characteristic wavelength. That's true in the sense of all spectroscopy, right? So the option C and D that are true here. Okay, but A and B are not true. Okay, now uh, another question. Okay, Q5. Match the technique in group 1 with their application in group 2 for protein analysis. So here you have to find different kind of application. Okay, so here one is nuclear magnetic resonance. You already know that NMR, through NMR you can predict structure of molecule, 3D structure. So I am writing here 4. Now here you know ultraviolet spectroscopy, UV, that for concentration estimation. So DNA, RNA, any kind of concentration estimation, that use Beer-Lambert law. So here I am writing 2. The DLS, to DLS you can get to know the size of molecule, size. Dynamic light scattering, that's all about size. So here I am writing the 3, and the remaining Fred is the fluorescence resonance energy transfer, that depends on the proximity to molecule. Suppose this is energy transfer, that also start used for studying protein-protein interaction in membrane. Okay, so here it's 1. That means P4 and Q1, R2, R2 and S3. So B is the correct answer here. The technique that involves impacting samples with electron is NMR. Here we are using no electron. It's all about IR, radio wave. Sorry, it's all about radio wave. ESI, we'll check it later. IR spectroscopy, nothing. It's all about IR. UV visible. Here we can't say there is some direct implication of electron. So in ESI mass spectrometry, in mass spec class we will learn. So here we have to use electron. So ESI mass spectrometry you have to use electron. Okay, so here the question is saying solution of following peptide are prepared according to concentration of 1 millimolar. Among these 4, which one has the highest A280? So protein absorb A280 due to 2 amino acid, mainly tyrosine and tryptophan. Also phenylalanine is there, but it absorbs mostly at 260. So these two molecules, or all these two molecules, are aromatic amino acid. aromatic amino acids. So just assume if in a peptide the amount of tyrosine tryptophan is high, that means that peptide will show highest A280. So here we have to check the number of tryptophan and tyrosine. In A, number of tryptophan is 1 and phenylalanine is 1, tyrosine is 1, tryptophan 1. That means tryptophan 2, tyrosine 1, phenylalanine 1. In case of B, there only phenylalanine is there and 1 tyrosine is there. In case of C, 1 tryptophan is there only. In case of D, only phenylalanine is there. That means in A, tyrosine, tryptophan, phenylalanine both are present. That's why A will be the correct answer. A will show the highest A280. Highest A280. The purity of plasmid DNA preparation is determined by analyzing the ratio A260 by 280 in a pure DNA preparation. So I already told you, suppose just draw this 0, 1.8, 2. This is for DNA. This is for RNA. That's 0.6. That's for protein. Right? Now, if in between something, that means you can say DNA has RNA contamination. But as the options are not here exactly, so we can say it's close to 2. The purity of plasmid DNA determined by analyzing it 260 by 280. In pure DNA, it will be 1.8. Right? That's close to 2. Okay. But remember, if it's showing 1.98, something like that, that means your sample has RNA contamination. RNA contamination. Now, which of the following are not electromagnetic waves? X-ray, beta ray, alpha ray, cosmic ray. Of course, cosmic ray. Cosmic ray is not electromagnetic wave. Now, the NMR major limitation of using NMR to determine protein structure is resolution is poor. It's not exactly true. Resolved structure is not reliable. No, you can rely on the structure. Difficult to interpret the data for larger protein. Yes, that is difficult to interpret data for smaller protein. No, there is no difficulty. So the exact answer is 3. So we already discussed that for larger protein it's quite impossible to solve the structure through NMR because of the huge spectra data, right? Now another question is that given 3 samples, L-tyrosine, D-tyrosine and equivalent mixture of L and T-tyrosine, which one following method can help in identifying the samples? UV absorption, no, it's not actually. Here you will get only the concentration in 0.6, 0.8 something. IR spectroscopy, that will tell you about a functional group. Okay. Optical rotation can be okay, but the mixture it's quite not possible. So NMR spectroscopy, so through NMR you can say, because NMR will deal about the configuration of molecule. So through NMR you can say that what kind of sample it is. Okay, so that's all for today. So please let me know if you have any doubt, and I'm requesting you please go through the slide and the PPT and I will share in the group, and so that you can understand and everything that is important for you for IT jam and GATB aspect, everything is discussed in the class. Okay, see you, bye.